the information. You all are being recorded right now, so please be careful. Okay, I hope all the people on the Zoom are able to look at the screen as well as I have enabled the video as well. If you skip out on the board, I'll direct the video screen towards that so that you can also see that. So today's discussion will be very, very interactive. This is what actually I want. I hope interaction can only be possible if people here actually ask questions, stop me wherever they want to, and if they have any thoughts around like what do they know about, or they want me to specify something or go deeper into a certain area, I will do that. Asking questions is totally fine. No question is a naive question or dumb question, etc. But I may not have all the answers, so I have the possibility of not giving you the answers right away if I don't know it, but you can ask whatever you wish, as long as it is pertaining to machine learning or AI or the related areas. That's what we are going to do. The reason why I chose this topic to be shared with the rest of the folks today was that we particularly, like me and my team, are focusing on feature ecosystem in particular, and feature ecosystem, as you will learn as we go forward with the presentation, is one of the key critical portions during the entire machine learning life cycle. So it made sense for us to understand the entire end-to-end story, how the overall machine learning goes, and there are a lot of buzz in the industry around machine learning, artificial intelligence, deep learning, etc. So this is an opportunity for us to just go through it, know what's going on in the industry, how Capital One can benefit, what we as a team are doing, and how we contribute to this ecosystem. That's the agenda for today. This requires no prior understanding of machine learning or artificial intelligence, etc. So if there are people who are already experts in them, please pardon me that I'll be repeating some of the things that you probably already know. But mainly the intention was to start it without making sure that you do not need any prerequisites other than if you have heard about maybe machine learning, artificial intelligence, and things like that. So that's the idea for today. Before we begin, any questions, any area you would like for me to really focus upon? I do have a presentation, but I don't have to go with this. I can go with specific areas if there are any that you would like me to focus upon. Anything from the crowd on Zoom as well as here. And please speak up because I'm far away from my computer, so if you're typing something, I'll not be able to see. I have a presentation listed here, so please speak up if you have any specific areas you would like for me to go deep into as we start. Anyone? Everyone seems to be okay with whatever I have here. I hope the same is true for the people on the Zoom as well. Okay, we'll start. So as you can see from the definition here, this definition was coined about half a century ago. As this can tell you how old machine learning is when it was started. That the ability for us to make computers program themselves or be able to make critical decisions based on the data provided to them is machine learning. So essentially, the idea is good. We are just starting, so we're not right now. So the idea is that I would like to first of all go with expert systems. Have anyone here actually heard about expert system? Has anyone heard about like what an expert system is? Anyone has any idea? Anyone on the Zoom, in the class or in the Zoom? Anyone heard about what is an export system? Any idea? Never heard about that word? Yeah, go ahead.
To export biases from a data set.
Sorry, come again. Can you
to export a bias from a data set, or to identify benchmarks.
Okay. So the export system is to export biases from the data set, and what was the other thing you said?
To set benchmarks.
Set benchmarks. Okay. Does anyone else has anything to say? People who are on the video call, they are very silent audience. Okay. So an export system is something that you program. So if you have ever heard about like an embedded system, so when you go for, let's say, has anyone used a Nest device in their home?
Yeah.
Someone may have used it, right? New York maybe it doesn't have like a lot of the updated homes, so people
I've
don't.
seen it. Yeah,
Seen it.
I don't have one. But.
Okay.
I know people who use it.
Yeah.
So in other places in the world, people use some automated systems and things like that. And Nest could be considered as one of the embedded devices. when I say embedded device, is a device that, so your phones, we all use phones, okay, this is an embedded device, meaning the following. An embedded system is nothing but like a operating system, like a software system that has to work exactly the way it has been programmed to. There cannot be two things about it. And that is why most of the embedded devices have a real-time operating system inside it, not like general purpose operating system, which we use on building servers and things like that. The second thing is embedded systems are generally very, very small and compact because they have to work in a very limited area, such as your phone, which nowadays have very large memory, but a Nest device, etc., could have very, very limited memory. So, and expert systems were first programmed. Basically, you go with an algorithm, say if, then, else, 1, 2, 3, 4, 5, 6. These are the steps that it has to take. Expert system will exactly do one by one, step by step. So basically, you program the code, and the system works exactly as per that program. Since you use real-time operating systems, etc., for an embedded system, it has to operate exactly that way. It cannot, like, there cannot be any assumption of latency. There cannot be any assumption of things can go wrong or not happen. In a general purpose operating system, there is a possibility, especially because the context switching takes time. In a real-time operating system, it doesn't, because text switching is very, very fast. So an expert system is that it behaves exactly the way you program it. Now, things such as, you know, your embedded devices, even your, you know, phone call, like you get a call, it always rings. You will rarely find a, you know, situation whereby incoming phone call is coming and the phone doesn't ring. It generally never happens. That's what the expert system is. However, when you program software in a general purpose server, etc., many times you have issues and bugs where certain things do not function the way we desire them to function. That's the major difference. So how machine learning is different from an expert system? So the point to focus on is machine learning is not a programmed system. So machine learning focuses on data. So give a lot of examples, what has happened in the past, and machine is supposed to extract the formula or extract the program out of the data. That's the key major difference. So what we have learned in computer sciences, or when we go to study, we learn about programming and how to program a system. Now, if we were to just give some examples of, hey, this is what has happened in the past, can the system, derive, interconnections between those data points and build a formula or a program for it? That's roughly what machine learning is trying to do, right? So that's the major difference. So you do not program machine learning right away, but you program a system, which is an expert system or a general purpose program. So you have to write the step-by-step steps, what needs to be executed. In machine learning, you expect the system to uncover those relationships and program from the data that you present to it. Now this seems like magic. Like, really? I just throw in data and system will figure out what relationships are and will produce results? How is it even possible? Well, that's where the machine learning comes in. So essentially what happens is there are specific set of algorithms even for machine learning that has been defined earlier. And basically the job of the human is to choose those algorithms. As long as you choose the right algorithm and provide the set of data, the new formula or the new program that the machine has to build, it will build by itself. But you have to give it a starting point. That is the algorithm. So basically you specify that, hey, I like this algorithm, I'll give this algorithm, and I'll present you a bunch of data points, what has happened in the past, and you are expected to give me a relationship that tomorrow if something happens in the future, what is the outcome that will happen? So you have to build that. So the machine built program is known as model. So in machine learning, when we often talk about the machine learning model, the model. Model is nothing but the program that machine builds based upon two inputs, the algorithm that you choose and the data that you give it to it. So that's how the machine learning operates. So since I anyway have the slides, I'll go through it, but most of the time I'll talk. So these are the three types of machine learning generally people talk about and work. So on the very left is your supervised machine learning. Then you have unsupervised machine learning. And finally you have reinforcement learning, where a lot of focus has been more recently. Especially if you have heard about, the Go game that, one of the Google's, they built that using reinforcement learning, and it beat the, highest skilled player in the Go game. Go is supposed to be the most complex game ever. I think 100 times more complex than chess. It's generally played in Southeast Asian countries. So Google built that system that used reinforcement learning to beat the most key player in this environment, and hence it became very important. So so think of it like this. The supervised machine learning focuses on when you have a lot of labeled data. Labeled data meaning, like, let's say this is capital 1. Capital 1 most recently was exposed to one of the, let's say, cybersecurity theft, right? Just recently we've seen about it, right? So I'm assuming that there would have been systems that would be there to detect such kind of intrusions. So most likely in this case, what would have happened is that when the person or the system who would have intruded would not have gone detected, meaning machine learning would not have classified that intrusion as fraudulent or suspicious. You're getting my point? So any traffic that comes into the system goes through whether this is suspicious traffic or not. This is kind of predicting whatever is coming. Is it like fraudulent? Is it suspicious? Is it malicious? And I'm hoping, I don't know the answer for that, but I'm just thinking maybe the current systems that were deployed did not tag it as that, and hence they were successful in doing what they were able to do. This is just one of the examples. Same way, this company has a lot of credit cards, right? And a lot of people use credit cards, but we also have questions of credit card theft, identity theft as well. So how do you ensure that the person who is the actual owner of the credit card is the one actually using it and not a kind of a thief or somebody like that? So in those cases as well, you have something like a supervised learning system that validates each transaction. Is it fraudulent transaction or not? So you might have yourself experienced, let's say you live in New York, but let's say you're traveling to, let's say, San Francisco, and you swipe your card. Sometimes you'll get a call from your bank saying that, hey, are you the person who used this card? Because you're now no longer in your local area where you are used to doing transactions. Or sometimes you go to some, site which you have not ever visited, or it's like not necessarily very good site. And the system has never seen it before. So if you are trying to do a transaction on that website, again, it will put a authorization hold on your card, or they'll send you a text or try to call you, hey, are you making the transaction right now online? Those are the real-time fraud detection systems. Some companies do. I am hoping many banks already deploy that. So those are like real-time supervised based machine learning systems in action. I'm just giving you those real-time examples that happen most of the time. How would you build such kind of a system? The question arises is this. So basically what happens is, to build a supervised machine learning system, all you need to do is, you need to have several examples of past. Like in the past when these transactions occurred, these were found to be as fraudulent, and these transactions were found to be as good transactions. So you need to have a list of all the bad things that has happened, all the good things that has happened. This forms your training data set, the combination of good and the bad. You feed it to an algorithm, which I'll describe in the next few slides, like what are some of the algorithms that you can use to build a model. Once the model is built, now whenever a new transaction comes in, you just feed it like a RESTful API call. Here is a model, you send it a request, a feature vector to it. As an output, it will say, this seems to be like fraudulent, 80% probability. This seems to be fraudulent, 60% probability. So it will also give you a confidence score, like how sure I am this is definitely fraud or not fraud. Based upon that, you can take a further action. So when it is 90% fraudulent capability, you can immediately block that transaction. When it is 60% fraudulent capability, you will put an authorization hold and invoke a automated response, sending a text to the customer to approve or disapprove the transaction. So you can take, so those workflows can be based upon your scores. Like what is the prediction that came out, right? So those are some of the things that happen. So that's what the supervised learning is. So you need to have, so the challenge with the supervised learning is that you need to have training data set, meaning you should already be having examples of good transactions and bad transactions before you can build a model. If you don't have, then you can't do it. And you should have labeled data. Labeled data meaning you should know, okay, this transaction was good, this transaction was bad. And once you have new transaction where you don't know whether it is good or bad, that's what it will get predicted. So that's the challenge with the supervised machine learning. So you need to have a lot of training data set with good, bad, etc. Now, unsupervised learning. Many times in the real-time use case in the real-world examples, right? You always don't have labeled data. Like you will have data, a lot of data is there, but you don't know whether this is fraudulent data, good data, etc. You don't have any kind of label. What do you do there, right? So there comes for rescue unsupervised learning. That's the second branch of machine learning. So here basically what happens is that you still want to uncover some kind of insights from this data, and to do that, unsupervised learning is used. Some of the algorithms that are very popularly used in unsupervised learning are clustering algorithms. So basically you are thrown, so for example, let's say there are a lot of calls that come into a call center, like customer service reps are there, they receive a lot of calls from a lot of people all around the globe, and they come into, let's say, a single queue. You have 10 customer support agents that actually are working on those calls, and they are responding to that. Now, one of the, let's say customer support agent manager decides that, this is not a very efficient use of my time. I would like to specialize my customer support agents to focus on different areas. And let's say the person says, I want to figure out what those areas should be where my customer support agent should focus upon. Because calls can come in, hey, I have billing question, I have credit question, my credit card got stolen, I have a question regarding that. As you can imagine, people can ask multiple kind of questions from a customer support agent, right? And one customer support agent may not be capable enough to answer all kind of different questions. So the logical thing is that if I specialize my customer support agents, hey, one will focus on billing, one will focus on onboarding, one will focus on fraud, another will focus on risk, etc. This way I can train my customer support agent to better handle my customers based upon what kind of questions they are asking, right? So we have something like use case, right, which answers the questions and answers for different kind of people. Same can be applied here. So in those cases, what could happen is that with all the incoming number of questions that customers are asking from these customer support agents, typical unsupervised learning clustering use case could be that cluster this data into various key classes. So basically all the incoming number of questions are coming in. You apply a clustering algorithm to it, unsupervised learning. All it will do is try to find out what are something similar. So it will build clusters of similar looking questions. And that could be your starting point. So maybe they'll cluster all the fraud-based questions together, billing-based questions together. I'm just using this as an example. That's not exactly how it will do it, but this is one of the ways unsupervised learning or the clustering algorithms actually work. So now you can imagine when you have vast amounts of data, but you don't know how to start or how to organize the data, clustering comes into your rescue, or unsupervised learning. That's one of the examples. Reinforcement learning. I'll just touch upon this topic, but will not go in super detail in this one because that's something we are not using here, so it may not be of much more relevance. But since it is one of the types of machine learning as well, and it has become super popular, I'll anyway speak about it as well. So generally, this reinforcement learning is much more recent. It didn't exist several decades ago, whereas both supervised and unsupervised have been there for several decades, as I showed you on the first slide, that even in 50s people were working on machine learning. So reinforcement learning focuses on a very different paradigm. So they focus on the actor, basically the person or the system that is involved, how it responds with the environment where they are operating. So in case of let's say a video game, I don't know if Super Mario Bros. has a very simple game, right? So Super Mario Bros. Used to be, so basically that's the Mario is the actor here or the subject, and the game environment is the environment where the subject plays. So when they jump on a turtle or a duck, that's points, you gain points, and you don't have to touch them because it's either your Mario will become small in height or it will die, right? This is the life. So that's basically, you can see, and then there are coin symbols. When they hit that, they make more points. So that's like reward. So if you do positive things, you'll get reward. If you do negative thing, you'll get negative marks. That's exactly how reinforcement system works. So basically you have a subject and an environment, and subject has to interact with the environment. And at every step, whenever you take steps, you have positive rewards or negative rewards. You get my understanding, following me? Mm-hmm. Based upon this, the character has to choose the path where they can earn the maximum rewards and minimize the negative rewards. So basically, you'll, as the end of the day, you will sum all the rewards that they have got, plus minus, and finally, if they have higher sum, that's the right thing to do. So that's how a reinforcement learning system works. And generally, as you can see, in simulations, in games and all, this seems to have played very good role, right? So that's what the reinforcement learning is about. Any questions so far? I'm fast, slow, all good, not good? all bouncing above the head. I'm hoping people on the call are probably following it as well, but please feel free to ask any questions. So these are the categorizations of machine learning. I actually this is a different way of classifying them. So I have removed the reinforcement learning. It just focuses on the supervised learning and unsupervised learning. So now some of the things are very, very important here, which I would like to focus on a little bit. So there is something known as continuous and discrete. So anyone has any idea about what continuous and discrete would mean here? Anyone, any thoughts? Yeah.
I think continuous has a infinite amount of values that it can be, and discrete has a specific amount of values.
Yeah. So this is one way of describing it. So one of the ways of thinking about it is discrete is when you have specific set of values, and continuous is like there is like from 0 to 1 there could be infinite values because it is all fractional numbers. But if I say I can only have integers, then there are only 10 values, right? But does it make sense? That's the discrete versus continuous horizon. So classification, so within the supervised learning, the classification concept focuses on when your output, the things that you want to predict are discrete, then you use classification under supervised machine learning. So I'll do some whiteboarding here also just to explain if I have some pens or yeah. So basically within the what we learned earlier was supervised learning. So within the supervised learning, when you have discrete outputs, so when you already know about a fixed set of classes that you want to predict, that's when you use classification. So this is considered as classification algorithms, and there are a bunch of them which I'll share as we go forward. Classification is of two types. Binary classification, as the name suggests, when there are only two discrete classes, yes, no, true, false, binary classification. And next is multi-level classification, high, medium, low, more than two classes, multiple level, very, very simple concept, nothing like no data scientist kind of thing, very simple here, right? So binary and multi-level classification. Now the point to note is discrete. So when I say discrete classes, meaning that either the answer can be true or it can be false. It could be 0 or it could be 1, high or low, something like that, right? So whenever I have just two answers, like binary answer, then it is binary classification, and you can tell either your prediction can lie in class this or class this. There can be no other alternative. If not this, then it has to be this. It's very straightforward. This also, so binary classification also happens to be the most accurate ones. So people build several models and things like that, but whenever they build their problem like a binary classifier, that seems to operate much better than if you were to build a multi-level classifier. Anyone has any thoughts why that might be the case?
Easier to derive what's true or false because there's less options to fall in buckets for.
Exactly. So if you have, let's say, 3 buckets, right? High, medium, and low, right? Or maybe you got 10 buckets. So if you correctly predict it is there, then you are good. But if you don't know this is the answer, then answer could be here, answer could be here. There are a lot more options to go wrong. And that's the reason that whenever you build multi-level classification, generally the accuracies are not as good as you would get in a binary classifier. So this is, I'm just saying through practice. I mean, and most of the times when you are trying to do it, the good thinking is that can I frame this problem as a binary classification problem? So I'm just giving you this as a hint. Like whenever you plan or think about problem, think it this way. You can still do this way as well, but generally you'll not get very good accuracies. And I'll talk about like what I mean by accuracies and things like that. So a classic case will be everyone uses one classification, at least in this room. I can bet everyone uses. What is that example? Can anyone quote? All of you are using it as of we speak today. Which can you give me an example? Which one is that?
Gmail.
Gmail, yeah, good. Do you know which specific, like what happens?
The tabs for like promotions.
That's one example. There's another one.
And spam.
Spam.
Exactly, spam filtration is a classic example of which has been used by everyone now. Whether you use Gmail, Hotmail, Yahoo, whatever. They may not be that accurate. Gmail seems to be very accurate, but that also brings. So basically, what they try to do is they are trying to. So whenever an incoming message comes in, they want to either send it to your inbox or to your junk folder. So these are the two classes they want to. And as you said, priority, etc. Now they have multi-level classification also. So they have priority mail and what else is there? Priority and
Like
promotions and
yeah.
social or something like that, right? So they do those kind of classification as well. But many times you will see these are not very good. But junk and inbox is like really good. You can yourself see it in Gmail itself. Here they'll keep doing wrong. They'll set it in updates. Sometimes it goes in social. It's all over the this thing. So that itself is. So when Google can do it wrong, now you can imagine, right? Sorry. So basically, this is what I was trying to focus upon. So classification, binary seems to work well. Multi-level classification, you can still do it, but chances of getting accurate results are much more harder to arrive at in multi-level classification. So I also want to illustrate another point here. Since now we all understand the email classification problem, filtering the incoming text as inbox or into junk. So basically, incoming mail comes in. Here is the classifier, spam classifier. Either it will tag it as inbox, which is basically good, or junk, basically spam email or something like that, right? These are the two tags that can happen. Now, one way of looking at the accuracy of the system is that, let's say a new message comes in, right? Now, if suppose this is a good message, but Gmail actually classifies it as junk, is this acceptable to you? If I classify income, let's say this is mail comes from your manager, and Google thinks it is junk, and it classifies it junk, and hence this email sits into your junk folder. That's fine. Or let's say I give you a choice. Either this can happen, or the second thing can happen is there could be another email that is actually bad, like some marketer would have sent you this mail which you did not intend to or you did not subscribe for, but then Google classifies it as good, and hence this mail sits in your inbox. So you can either get a junk mail in your inbox, or you can have your good mail sit in your junk folder. Which one is better use case for you? Let's say you can only choose one or the other. You can't choose both.
The bad message in your inbox.
Bad messages in your inbox is better for you.
Yeah.
And good messages sitting in your junk is acceptable to you.
No, it's not acceptable.
Not acceptable to you.
Yeah.
So I'm saying you can only choose one. You can't have both. Choose one. Like, what is more acceptable to you? Like, are you okay that some of your good messages can go and sit in junk, or are you okay some of the junk messages come and sit in your inbox?
Ladder.
So you're okay with some of the junk messages can come and sit in your inbox?
Yeah.
So okay, I'll let Google know that you want it that way. Okay. Yeah. So basically, this is what describes that. What do you really care about? That's what describes the accuracy of your system. So if you choose, because as you can imagine, as we'll explain further with the formula, that you can't. These are two orthogonal to each other. Orthogonal meaning that if you try to minimize one, the other thing will go high. If you minimize that one, this thing will go high. So essentially, you cannot optimize both. So this is known as false positive and false negative actually. So I'll illustrate it with further example, but this is a great example here. So basically, if you try to minimize the number of junk to actually come into your inbox, at that point of time, you cannot actually. So basically, in this case, actually, we are actually minimizing the false negative rate primarily, so that we can ensure that at least in our inbox folder, basically we don't have. So in the inbox folder, we can have some of the junk messages, while we want to ensure that none of the good messages can go sit in the junk folder. And the reason for that is you do not see your junk folder so often. So if at all an important message goes and sits in your junk folder, there is chances that you can just ignore that thing and you will lose important message. We already discussed about clustering. Same way, we introduced the topic of classification. The next topic I wanted to introduce was regression. So regression is also a supervised learning. The only difference here being is similar set of algorithms are used for regression as well. The only differentiation here is regression predicts continuous data. So we talked about discrete classes and continuous classes, right? So whenever you are doing something like forecasting, whenever you are doing like weather prediction, right, or stock price movement prediction, etc., that's like forecasting. That's regression, because you are actually specifying exact numbers. So they cannot be fit into like a class. They can, but then that will be a classification problem. You can say, hey, the stock price will go up or stock price will go down. This is classification. But if you specify, hey, stock price will go up by 2%, by 10%, by 5%, that's regression. Make sense? But you use similar setup. So it's supervised learning, but based upon the output, you define whether it is regression or a classification problem. And majority of the times, you can define a problem as the way you like. You can make it a regression problem and you use regression algorithms, or you make it classification problem and you use classification algorithms. Generally, those algorithms are also similar, which I'll talk about as we move forward. So far, so good. Are we on the same page? Supervised learning, right? So on the unsupervised learning side of things, we already talked about clustering. When you do not have labeled data, you just have thrown a lot of data and you want to say, hey, uncover some kind of interesting insights from this data. So I can cluster them into small groups, and maybe those will give you insights. Like I talked about earlier, that customer support agents are getting a lot of emails, and you have just millions of emails, and you just cluster them into different hotspots, etc. And they use again algorithms in that to arrive at those what those hotspots are, etc. There is another thing, dimensionality reduction. So within the machine learning space, right? Generally, what happens is that when you are trying to build a model, especially in the case of supervised learning, you have to use a lot of data. So data would be typically, basically, like a simple CSV file, right? Where you can think of it as a CSV file, where this is like the predictions or the labels, we talked about, right? It could be yes, no, binary classifier, something like that, right? So here it will be yes, no, yes, no, yes, no, yes, no, etc. And here will be all the data fields that you are interested in. So here will be your features, F1 to Fn. These features could be like age, marital status, what is your credit line length, how long you have been a customer with this company, etc. So based upon whatever model you are building. So basically these could be your different features that are coming in, right? So as you can imagine, I can have n number of features, n meaning 10, meaning 100, 1000, million features. Now we all work in the data space, right? So if I have to crunch this file, which can have millions of features and as many examples of them, like again millions of them, this becomes a pretty huge data set. So if I run it on any machine or computer, it will take a lot of time, right? Wastage of resources, time, etc. Right? There is no shortcut to it. Whether I used EMR, Hadoop, whatever, it is still, you have to compute everything if it is there, right? So there is another set of algorithms that have been derived. If and we know, right, every feature is not a good indicator of actual response. Let's say I wanted to predict fraud. Then does your name really is a good indicator of fraud? Maybe it is, but does it look like it? Maybe not, right? So maybe one of the feature here is name. Maybe you can eliminate it. It doesn't signify anything with respect to fraud. There may be another feature, let's say it talks about zip code. Is it a significant feature for fraud? Maybe it is, because some zip codes are known to be fraudulent. In US you can't use it, but generally people know that that's the case. That's how some of the zip codes, generally in many countries, they will not block the transaction. So in US also they block embargo countries like North Korea, Iran, etc. So any traffic that comes from those locations, they will not accept. So that's a good indicator of possible fraud. So you would still want to keep that as a feature. Maybe another feature somebody has used, it says whether this person is married. Maybe that's not a good indicator of fraud or not. What does it has to do whether the person is married or not? So basically, you can have multiple features like that, but not all of the features will be relevant to you or good to build this model. So what dimensionality reduction does, given the set of features that are there, it will bring out what are the most important features required to build your model. So earlier you had, let's say, 1 million features, it will drop it down to, let's say, 100 features. You see what I'm saying? Does it make sense? So basically you're reducing your space of computation. So some of the algorithms used for doing that dimensionality reduction are like principal component analysis, LD, etc. We'll talk about some of those algorithms that are given later. But this is what it does. So I'm just signifying like why each and every space is important, what it does. So given that you have like, in case of like Discrete, right, it has 250 features and they are very, very complex features, right? Not every feature will be required by every algorithm. But if you say, hey, I want to build a model that uses every feature, then it will be so much of computation and it may not be even valid for you. So you can run like a PC algorithm that will pick and choose the prominent features from it and discard all the irrelevant data. So that's the helper. That's what dimensionality reduction is. So from your feature space of 1,000,000, it reduces it to 100 or 5 or 3. And this is how generally PC principal component analysis. This is how it works. It says it stack ranks all your features. So it says feature 1 gives you 50% of your predictability. Feature 2 is almost 30%. Feature 3 is 10%. Feature 4 is 50, 30, so we are already 90, maybe 5%, and then remaining rest of the features are total is 5%. So you may completely discard these features, but they do not have that much of prediction power. You get my point? 95% of your results are just based upon these 4 features. So it stack ranks all of them. So you can discard the long tail and just focus on the top features that are giving you the results. That's what dimensionality reduction does. So far so good. So we talked about supervised learning, unsupervised learning, within supervised learning. If you have discrete outputs, it's classification. If you have continuous outputs, it's regression, or regression examples are whenever you are doing forecasting, weather prediction, etc. When you are having continuous numbers as outputs. Classification is when you have specific classes. Hey, cluster these set of customers in high, medium, low risk. These are like 3-level classifier. Binaries, yes, no, true, false kind of a thing, fraud, not fraud, spam, not spam, etc. So now moving forward. So these are some of the popular machine learning algorithms. If you can, so specifically within the ML space, you have support vector machines, decision trees, which has been very, very popular. People do it. It's like a tree structure, so people generally understand it really well. It's always like yes, no, and you keep further going down the tree. That's how it computes. You have randomized forest, which is a bunch of trees together. That's a random forest. You have a knife base knives. Several set of algorithms are there, so you can read about it as you want, but each algorithm has a particular way they are implemented, and that's what I was saying. So basically you give set of data that I showed in the data set, apply one of these algorithms, and that gets you a model. So basically this is how machine learning is done. So given a data set, labeled data set, apply one of the algorithms that are listed there, it will throw you output with a model, and that will be your computer generated code. That's how machine learning operates. The DL with what I refer here is deep learning. So I'll now introduce the concept of deep learning. I will not go in detail of it, but I'll introduce it because nowadays people talk about deep learning, so we need to know about it. So within the computers, right? So some of the algorithms that are listed here are basically traditional machine learning. So support vector machines, random forest, Bayesian networks, a decision tree, random forest, etc. These are traditional way of machine learning. People do it, and some of these algorithms have been there for decades, if not anytime sooner. Deep learning is much more newer concept, and they're specifically focused on a subset of machine learning, which is artificial neural networks. Even artificial neural networks are 50 years old, or even longer actually. They were invented then. However, in those times, those neural networks were having very limited number of layers, like 1 layer or 2 layer or 3 layer networks. When we talk about deep learning, these number of layers can become n. So there could be tens and hundreds of hidden layers. The more the layers, the more complex the network becomes, right? And as the number of layers becomes more, it also becomes much more difficult to comprehend what the algorithm is actually. So what algorithms we have listed earlier in the machine learning, these are basically some mathematical formulas that are there, and